All right, so chapter 5 is when we did probability. Chapter 5 was the probability chapter. So we went from a chapter that was all writing and no math to a chapter that was almost all math and no writing. Law of averages, not true. Future outcomes are affected by past outcomes is what the law of averages are. This is not true with probability. If I flip a coin 5 times and I get heads 5 times in a row, that doesn't mean I'm more likely to get tails on the 6th flip. What happened before does not change the fact that every time I flip that coin, it's a 50-50 chance. Law of large numbers is true. Law of large numbers says if I flip a coin over and over and over and over and over, and I do it 1,000 times or I do it 10,000 times, approximately half of my tosses will end up being heads and approximately half will end up being tails. So the longer the run, the greater the true outcomes match the theoretical probability. And then we have our general addition rule. That's what this is right here. Does anybody remember what this upside down U means? Union, which is the same thing as an OR. Union, we're putting things together with an OR statement. If I want to know, are you wearing a black shirt today or are you wearing white shoes? If both conditions are satisfied, then you meet the criteria, or if only one of the conditions is satisfied, you meet the criteria. So it's this or both for an OR. We call it an inclusive OR. And the upside down capital U would be what? The AND. We call this the intersection. So for an OR, what we would have shaded is both circles. For an AND, it's only going to be shaded where they overlap, if you're looking at Venn diagrams here. Conditional probability. We read this as A given that B. We calculate the probability of A given that B has occurred by doing the AND over the given. So the probability of the AND divided by the probability of the given. When we have mutually exclusive events, this Venn diagram shows a pretty good picture of what mutually exclusive events look like. Where do they overlap? They don't. Mutually exclusive events, if it happened with A, like if event A happened, event B did not. If event B happened, event A did not. They cannot coincide. They cannot happen at the same time. So we say the intersection is equal to 0. Venn diagram, you want to start with the middle if possible. And we'll look at an example problem today that I would solve using Venn diagrams, and I will explain what I mean by start with the middle. But anytime you are looking at a Venn diagram where there is overlap, like this, to find the probability of A, you would need everything inside the A circle. So that would include the overlapping space added to whatever is not in the overlapping space. Both of those together make the probability of A. All right, a couple things I want to add here. Something about independent events. With independent events, the probability of A given that B is equal to the probability of just A by itself. So the probability of A given that event B has occurred is exactly the same as the probability of A occurring whether or not B has already occurred. These two do not influence each other. With independent events, the probability of A and B occurring is equal to the probability that event A has occurred multiplied by the probability that event B has occurred. Make sure everybody's had a chance to get this copied down. Everybody good on these? Okay. Some interpretations real quick. The probability of A after many, many, many whatevers, the proportion of times that context A will occur is about blank. So the probability of heads equaling 0.5 means after many, many, many coin flips, the proportion of times that heads will occur is approximately 0.5. And then conditional probability, remember we read this as given that. So given that event after the line, so if pulled over is the given piece, the piece after the line, you say given that a car is pulled over, this event already occurred, there is a 0.48 probability that the car is red. So the probability of the event that comes right inside the parentheses, the thing that has already happened is the thing that comes after the line inside the parentheses. We know that event has occurred. It's no longer a probability of it happening. It did happen. All right, now I want to switch over to that white paper that you picked up on your way in the door. Decided to do this on paper instead of whiteboards today so that you guys have something that you can take with you, because probability tends to be one of those things that we do okay when we're doing it together in class, and then we leave and come back and we've kind of forgotten it because this is more formula-based and more procedural than several of the other things that we do in here. All right, so I'm going to start you off with this. The probability of event A is 0.35. The probability of event B is 0.6. And what's this? What's that upside down U mean again? And. The probability that event A and event B occurred is 0.27. I want you guys to find these three probabilities and then answer a yes or no on part D. I'm going to give you guys about 3 minutes or so to answer those 4 questions, and then we'll circle back together and go through them. Yes. Complement means not. You're welcome. All right. Complement means not. So how would we find the probability of A complement, the probability of not A? It's not the same thing as the probability of B. 1 minus the probability of A. If I tell you there's a 60% chance that it's going to rain today, what's the probability that it's not going to rain? It's 1 minus the probability that it does. So 1 minus the probability of A is equal to the probability of A complement. So we would do 1 minus 0.35, and that would give us what? 0.65, yes. So 0.65 is the probability for part A. Part B, what is this? Or. The probability that event A or event B occurs, we're going to use our general addition rule. This is the probability that event A occurs plus the probability that event B occurs minus the probability that event A and event B occur. You have to subtract the intersection because if you take the probability of A, that would include anything that overlaps with B. When you add the probability of B, you're including anything that overlaps with A. So you've included the overlap twice. Once when you did it with the probability of A and once when you did it with the probability of B. So we have 0.35, oops, not there, 0.35, there we go, plus 0.6 minus 0.27, which would give us what? 0.68. The probability of A given that B is the probability of A and B divided by the probability of what was given. In this case, that would be the probability of B. So what is the probability of A and B? 0.27. What's the probability of B? 0.6. So 0.27 divided by 0.6, which would give us what? 0.45. Are A and B independent events? What do you guys think? Yes or no here? No. Because the probability of A, given that B has already occurred, which we said was 0.45, is not the same as the probability that event A happened all by itself. That would be 0.35. And those two are not equal. If they came out to be equal, then we would say the events are independent. If the probability that event A occurs is 0.35, and it stays 0.35, if we already know event B occurred, then the events are independent. All right. Take a moment now and do example number 1. Suppose the probability that a construction company will be awarded a certain contract is 0.25. The probability that it will be awarded a second contract is 0.21, and the probability that it will get both contracts is 0.13. What is the probability that the company will win at least one of the two contracts? Give you guys a couple minutes to work on that, and then we'll go through it. Trying to find the probability that they will win at least one of the contracts. That means if they win the first contract, we're good. If they win the second contract, we're good. If they win both contracts, we're still good. This is the same thing as the probability of what? Of A or B, yes. So I'm going to say first or union, second. If you look up above at how we calculated the or, we used our general addition rule. So that would be the probability that they win the first contract plus the probability that they win the second contract minus the probability that they win both contracts. Let me scoot all of this over just a tiny bit. There we go. So the first contract, that'd be 0.25, plus the second contract would be 0.21, minus the intersection, 0.13, and we end up with the probability that they win the first or the second contract as being what? 0.33. This is a problem that you could solve using a Venn diagram also. If you didn't want to use the general addition rule, you can basically reverse engineer the general addition rule by using a Venn diagram to think your way through it. And this is where, on that yellow paper where it said start with the middle if you can, this is what I mean by that. So I would start off with the overlap, with the intersection, with the and. So this is where we would put the point 13. And then this circle here for the first contract, this whole thing added up together has to add to 0.25. I already have 0.13 in there, so how much more belongs in this circle but not in the overlapping space? If it has to add up to 0.25. 0.12. Now, if I were to look just at that blue circle, everything inside the blue circle together adds up to the probability of the first contract, that 0.25. And then we come over here to the second contract. This number that we're going to put in here, plus this 0.13 that is part of the second circle, has to add up to what? 0.21. So how much would go over here if these two have to add to 0.21? 0.08. So now when I look at just the second circle, this is everything that's inside the second circle, that adds up to 0.21. And then to get the union of those two things, we'd be looking at everything that is inside either one of those circles. And so we could add those three numbers together and we would end up with 0.33. So that's another way that you can think your way through this problem. You can use the general addition rule, or you can use a Venn diagram. All right, let's go look at example number 2. I would like for you guys to calculate these, or two probabilities, and then answer question C. What we've done up above will be helpful in answering these questions. What is the probability that a student from this group fails the math program? 0.1. You would do 200, the total of the fails, divided by 2,000, the grand total of the entire group, and you get 0.1. What is the probability that a student from this group fails the math program given that he or she has blue eyes? 0.1. In this case, we are only looking at that blue-eyed column. We don't care about any of the rest of this. And so there are 10 people with blue eyes that failed out of 100 blue-eyed people total. And we get 0.1. So then we get here to this last question. Are blue eyes and failing the math program independent or dependent? Independent. Why? That's exactly correct. Because the probability for fail is equal to the probability for fail given that they have blue eyes. Absolutely correct. So now we've seen one example where they're not independent and one example where they are independent. Let's go look at example number 3. Of the 60 obese teenagers in a recent study, 15 had type 2 diabetes, 20 had high blood pressure, and 10 had both high blood pressure and type 2 diabetes. Suppose one of these 60 obese teenagers is randomly selected. Given that the teenager has type 2 diabetes, what is the probability that he or she also has high blood pressure? That's part A. And then part B, if the obese teenager does not have high blood pressure, what is the probability that he or she also does not have type 2 diabetes? I'm going to give you guys a couple minutes to work on these 2 questions, and then we'll go through them. This is one that you can use the rules for, or you can make a two-way table for this to help yourself understand what's going on and how to set up the problems. So I'm going to draw a real quick two-way table here. All right, so across the top, we're going to have type 2 diabetes. We have a yes and a no. And over here, I'm going to put high blood pressure. Yes and no. We know how many students had type 2 diabetes, correct? How many? 15. So the total of this yes column would be 15. Out of a grand total of what? Out of a grand total of 60. So how many fall in the no category then for type 2 diabetes? 45. How'd you get there? Subtracted, yeah. These two numbers together have to add up to our grand total. All right, what else do we know that we can fill in? High blood pressure. Where would that go in the table? Looking at these 20 kids that have high blood pressure, does that go in here? No, that's a total for high blood pressure, so it goes over here. So we have 20 here. So how many here? 40. What else can we fill in? Yes, 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 type 2 and high blood pressure is 10. Well, if yes, yes is 10, how many are yes, high blood pressure and no type 2? 10, because it has to add up to 20. How many are yes, type 2, but no high blood pressure? 5. And so how many would have to be here in the no, no? 35. All right. Setting it up like this, I can now come back here. We want to know on part A, given that the teenager has type 2 diabetes. So we're looking right here. And we are only looking at numbers that come from that column. What is the probability that he or she also has high blood pressure? What would my fraction look like? 10 over 15. So 0.667, or 2/3. If the obese teenager does not have high blood pressure, so now this is what's been given. What's the probability that he or she also does not have type 2 diabetes? 35 over 40. 35 over 40. Anytime we have a condition at the beginning, it says given that, or they say if, and then they give you one of the conditions, you are only looking at that row or only looking at that column. And all of the numbers in the fraction that you're going to use have to come from that row or that column. So we have no to type 2 diabetes, that's the 35, over the grand total for no of high blood pressure, which is 40. And this comes out to be 0.875. So far, so good? Are there ways to do that with just formulas? Yeah. Making a two-way table makes it a little bit more explicit. You could also do this with a Venn diagram, but I already showed an example of doing it with a Venn diagram, so I wanted to have something slightly different. Plus, we had just done a problem with a two-way table. We can make our own two-way tables from the data. If we have two totals and the and, we can make a two-way table. All right, let's look at example 4. The probability that Michael misses a free throw shot is 0.1. if he goes to the line to shoot free throws due to a foul on a three-point shot, what is the probability that Michael misses all three shots? What assumptions did you make in order to calculate this probability? So what's the probability that he misses the first shot? 0.1. What's the probability that he misses the second shot? 0.1. What's the probability that he misses the third shot? 0.1. Are we trying to find a union here? Unions are when we add. We are not finding a union here, so we are not going to add. What operation do you think we're going to do with these guys? Multiply. So 0.1 times 0.1 times 0.1 would give us 0.001. What assumption did we make? We just took the probability of an event and multiplied it by the probability of another event, and then multiplied it by the probability of a third event. The only time I'm allowed to multiply probabilities together like that is we assumed the shots were independent. What is the probability that Michael makes at least one of those three shots? What'd you say? Not 0.9, but you're close. 0.9 is close, but it's not correct. 0.9 is the probability that he makes the first shot, because 0.1 is the probability he misses it. When we talk about him making at least one of the first three shots, that means he could make the first one, he could make the second one, he could make the third one, he could make the first two but miss the third, he could miss the first but make the next two, or he could make all three. Really, the only thing that we need to exclude is if he misses all of them, right? Do we know what the probability is of him missing all of them? Yeah, it's that 0.001. So I'm going to do 1 minus 0.001. This is 100% minus the probability that he misses all of them. We end up with 99.9%. What is the probability that Michael makes the first shot, but not the second or third? So we're going to do this one a lot like part A. The probability that he makes the first shot would be what? 0.9. And then we want the probability that he misses the second shot, which would be 0.1. Probability that he misses the third shot, 0.1. And then what are we going to do with all those? Multiply them. And we get what? Yes, 0.009. I'm going to set you guys loose on example 5, and there are quite a few parts there. So I'm going to give you, let's take somewhere between 4 and 5 minutes on question number 5. What is the probability that the selected student must take English? 0.7. You'd have 7,000 over 10,000, so 0.7. What about the probability that the selected student must take both English and history? What'd you say? 0.5, yeah. 5,000 have to take both out of 10,000, so we have 0.5. Suppose you learn that the selected student must take English. What are they telling you here? Given that they take English, this is a condition. What is the probability that the student must take both English and history? So the probability that they need to take history, given that we already know they need to take English. This would be the probability of history and English over the probability of just English by itself. What's the probability of history and English? 0.5 over the probability of just English by itself? 0.7. What is 0.5 divided by 0.7? I got something bigger than 0.35. Yeah, I got 0.714. Maybe just check to see if you typed it in. Got it, yeah. So part D now, if you guys notice, A, B, and C are all building on each other. We needed the answer from part A and the answer from part B in order to calculate the probability that they asked for in part C. And then part D builds on those three previous parts. It says, are the outcomes must take English and must take history independent? No. Why not? Yes, the probability of just taking English, or sorry, the probability of just taking history, my bad, just taking history. I didn't use my eraser like I intended to. Probability of just taking history is not equal to the probability of taking history given that they're taking English. All right. Answer the same question posed in part D if only 4,200 of the students must take both English and history. If 4,200 students have to take both English and history, that would recalculate part B here, right? So now the probability of English and history would be 4,200 over 10,000, which would be what? 0.42. And so if we recalculate the probability that they have to take history, given that we already know they're taking English, we would have 0.42 over 0.7. What is 0.42 over 0.7? 0.6. Is that the same thing as the probability of just needing to take history? Yes. Yes. They're independent. The probability of history given that English is equal to the probability of taking history by itself. All right, there's one more problem that I want to look at with you guys, and this is going to let us review another tool that we learned in probability, which is tree diagrams. Can you do it without tree diagrams? Sure. There's other methods that will work. You could do it with a two-way table. You could do it with a Venn diagram. I just happen to think that on number 6, a tree diagram makes the most sense. It lends itself to the way the information has been presented. So we have two people, Rudy and Fawn, that are each responsible for taking the daily tardy list. So we have Rudy and we have Fawn. What percent of the time is Rudy responsible for this? 0.30. 30%. So Fawn is responsible for it 0.70. And now they either get it there on time or they get it there late, right? Those are the only two options. So we have on time and we have late. On time and late. If Rudy was responsible for it, how often is it late? %, right? So that'd be a 0.10 right there. 10% of the time, if he's responsible for it, he's late 10% of the time. So what's the probability it's on time? 90%, if Rudy was responsible for it. And then if Fawn is responsible for it, what's the probability that it was on time? 92%, so 0.92. So what's the probability that Fawn gets it there late? 8%, 0.08. We want to know the probability that today Rudy is responsible for the list and the list was late. So let me select all this and scoot it over. We are trying to find the probability that Rudy was responsible for it, given that the list was late. So that would be equal to the probability that it's Rudy and late over the probability that it's just late. The probability that it's just late, I need to take this 0.30 times the 0.10. I need to follow Rudy's line and the late, and I need to multiply those together. So that's going to be 0.03. And then I need to do the same thing for Fawn. 70% times the probability that it's late, which would be 0.08. What is 0.7 times 0.08? 0.056. 0.056. And so the probability that Rudy was responsible for it and it was late, that's that 0.03. This is the probability Rudy and late. To find the probability that it was just straight up late, we take the 0.03 and we add it to the 0.056. And you should get 0.3488. Down here is the probability that it was Fawn and late. All right. We did this page instead of doing any FRQs because the FRQs that involve probability often have pieces of the question that's not just probability. It also gets into random variables or sampling distributions. So when we talk about random variables on Monday, we will get to some FRQs there.